Hi everyone, welcome to the PCD of Leetcode Biweekly Contest 148. This is TLE Eliminators and I am Pradyumn Kejriwal. So let's get to our first problem. Okay, this is not the first problem. This is the first problem. Okay. So the first problem is pretty easy. Given a circular array nums, find the maximum absolute difference between adjacent elements. In a circular array, the first and last element are adjacent. Yeah, so that they have given what is circular array. And so we are given a circular array nums and we need to find the maximum absolute difference between the adjacent elements. So like they have given examples. So we'll go through them. So in one case, the array is 1 to 4. So in that case, what would be the answer? Let's figure it out. Like 1 to 4. Now we have to report the maximum adjacent difference, right? So difference between these two is 1, between these two is 2, and since it is circular, so even these two are adjacent, so difference between them is 3, so therefore the maximum difference is 3. And similarly for the second example, you can see that difference between these two is 5, and these two is also 5, and the terminal ones, this one and this one, that is 0, so therefore the answer is 5. You have to report the maximum. So I think it should be pretty easy that like you just do what they say, you just do what they want you to do. Like basically you just run a loop from 0 to n and check the two adjacent elements. Like like if you have an array of this 1, 2 and 4, then you loop from I is equal to 0 to 2, and then you just check a of I and a of I plus 1, their difference. So a of I minus a of I plus 1, an absolute value of them. So absolute value of a of I minus a of I plus 1, and you just give a variable called max or ma or whatever, or answer, and you can just keep taking the max with ma. Okay. And but here make sure that if I is equal to like 2, then you have to do a0 instead of I plus 1. So what I did was just ai plus 1 mod n. So like if for the last element, so let's say it becomes 2, let's say I is equal to 2, then a of it will become a of I plus 1, like which is 3, mod n which is 3, so it will become a of 0. So it is quite a useful trick in circular arrays. Okay, so like this is the logic. I mean, there is no logic here, like it is just implementation. So I'll show you the code. Okay, so this is the code. Int diff is equal to 0, which is maximum difference. Now I loop through the like 1 to n, and diff is equal to max of diff comma these two numbers difference. So absolute of nums I minus nums I plus 1 mod n. So I take the max and return diff, right? So I hope it should be clear. Anyone who has any doubt? No, okay. I'm assuming not. So yeah, that was pretty easy. So let's move on to the next one. Okay, so the problem says that you are given two integer arrays ARR and BRR of length n and an integer k. You can perform the following operations on ARR any number of times. Split ARR into any number of contiguous subarrays and rearrange these subarrays in any order. This operation has a fixed cost of k. Second, like this is one operation, and another operation is choose any element in ARR and add or subtract a positive integer x to it. The cost of operation is x. So the return the minimum total cost to make ARR equal to BRR. And they have given a subarray definition. That what is subarray? It is the contiguous non-empty sequence of elements within the array. So yeah, one operation is this and other one is this, and each of them have a cost, and we have to specify the minimum cost to make ARR equal to BRR. Okay, so let's look at samples. Or okay, yeah, let's look at them. So ARR minus 7, 9, 5, and this is 7 minus 2 and 5, and k equals to 2. Actually, reading the samples won't give any insight. So in if you have any doubt in any sample, then we can discuss it. But I don't think it is beneficial to read it. Like it will get you far from the answer rather than closer to it. So I'll skip it for now. Okay. So actually, in this problem, what I thought was, first of all, this operation, it is like pretty sus. Like we can split it into any number of contiguous segments and rearrange these segments in any order. So like this is very flexible, right? And this has a fixed cost of k. Basically, we can give k a cost and do anything with the array. Like basically, it is very flexible, right? It is like Brahmastra. We can actually, it hasn't specified any size of the subarray or anything else. Like so, basically, what we can do is we can just take subarrays of one length. We can just split the array into subarrays of one length, right? Let's say we have some array, or let's take the sample only, or let's take some array, some random array, 3, 4, 5, 7. Then occurring like by giving k cost, we can actually rearrange this array into anything we want, because we can just split it into 4 parts. Like the subarrays that it talks about, we can just take singular elements as our subarray and we can rearrange them any way we want. Okay, so actually this k cost operation is very powerful. We can rearrange any the array ARR, like we can arrange the array ARR however we like using just k cost, right? And this x cost operation, that just means that we can decrease an element by x or increase it by x by giving x cost, right? So actually now the problem becomes that, so basically it is obvious that you won't do the first operation more than one time, right? If you want to rearrange, then you can just rearrange this array using this operation once. You can do it just by using it once. You will not use it multiple times, right? That has no sense. So either you use it or you don't use it, right? That's the question now. Like either you use this operation once or you don't use it. So if you don't use it, let's take that case. If you do not use it, then what will happen? The order of ARR and BRR won't change, right? Like if the ARR is, let's say, minus 7, 9, 5, I'll take the samples, minus 7, 9, and 5, and BRR is 7 minus 2 minus 5. So the order of these arrays, like, or the ARR array won't change if we do not use the first operation, right? So in that case, we can easily find the cost of making ARR equal to BRR, because at every index we want that element should be equal. So how do we do that? Like let's say in this index minus 7 and 7, so we need to add 14 onto this. Then we need to subtract 11 from this, and we need to subtract minus 10, like, or 10 from this. So like basically the answer is just absolute value of AI minus BI ka sum, right? ARR of I minus BRR of I, right? I hope it is, I think it should be clear. Like I'll still explain that to like to convert this minus 7 into plus 7, we need to add 14 into it. Then we need to, like, to convert this 9 into minus 2, we need to subtract 11. So basically the cost is like the absolute value of minus 11. So therefore we do absolute value of ARRI minus BRRI, like the absolute difference between the elements. That will be the cost to convert these elements, right? So we can just take the sum of I equal to 1 to n, and that will give us some cost. That will give us cost 1. Like that is the cost if we do not use this first operation, right? If we don't use first operation, then that is the cost. So let's name it cost 1. But what if we use the first operation, right? Then let's think about that case. Okay. So what will happen if we use the first operation? Actually, if you like as I told you, this first operation is very powerful. Using this first operation, you can actually rearrange the whole array into anything you want. Like you can rearrange this entire array into anything you want. So you have to figure out what is the minimum cost after some rearrangement. Like whatever you rearrange into, it will have a cost of k only. Like it doesn't matter what you rearrange into. Like you can convert this ARR into anything. Like minus 795, you can convert it into 5 9 minus 7, 9 7 9 minus 7 5, whatever. You can convert it into whatever thing, and it will have a constant cost of k. Like it doesn't matter what you convert it into, it will still have a cost of k. And then you will have to like make the arrays equal, like each individual index equal, so that will have a separate cost. So since this k is constant irrespective of what we rearrange this array into, we can just try to minimize this cost. We can try to minimize the cost of ai minus bi, right? This arr minus brr of I we had, and the sum of it we need to minimize, right? That's what we want to do. Like we want to rearrange the arr somehow such that this expression, like, or basically this expression is minimized, right? And final cost would be that minimum value plus k. So that would be cost 2. Now how do we minimize it? This is a question, like how to arrange the array so that our cost is minimized. All right. So let's see. Actually, this is a very popular question. Like I'll just tell you the intuition. Like okay, so let's say you have two arrays. 1 2 3. ARR is 1 2 3. Just 1 minute, guys. Yeah, so let's say ARR is 1 2 3 and BRR is 3 1 2. So tell me, what will you rearrange this ARR into such that this cost is minimized? What will you make? You need to minimize the absolute difference ka sum. Someone says 3 to 1. So what would be the cost in that case? Yes, 312, right? If you convert it to 312, then the cost would be 0. So basically you need the elements of ARR and BRR as close to each other as possible. Like let's say we have 1 2 3 and 4 5 6. 4 5 and 6. This is BRR. So actually this is the most optimal thing. Like what I'm trying to do, what I'm trying to say is basically let's assume another configuration of this ARR. So in this case, what is the cost? In this case, the cost would be 3 plus 3 plus 3, right? Which is 9. But what if we took some other permutation of ARR? Let's say we took ARR is equal to like 3 to 1, let's say. Actually, in this case, the cost doesn't change because I have taken the example poorly. Let's take some other example. let's take 1, 3, 5 and 2, 4, 6. This is ARR and this is BRR. Okay. So what is the cost for this? The cost would be 1 plus 1 plus 1, right? It would be 3. But now what if we had some other operation? What if we had this reverse ordered? So what if we had something like 5, 3, 1 and 2, 4, 6? So in this case, the cost would be 5 and 2, 3, 3 and 4, 1, and 1 and 6, 5, which is 9. So actually this 9 is greater than 3. So why did it happen? Because I put, like, I paired the far away elements, right? I paired this 5, 2, I paired this 1, 6. In this case, the closer elements were paired, right? 1, 2, 3, 4, and 5, 6. So actually I just need to pair it such that the sum is minimized. And actually that turns out to be that you need to sort both the arrays. Like if you just sort both the arrays and pair that way, then the sum would be minimized. Like if you can see here, sorting actually intuitively makes sense, right? Because let's say you reverse sort. If you reverse sort, then obviously the highest element of this array and lowest element of this array, they are matched together. So that is not very feasible. Okay. So actually the sorting is the answer. This is actually a very popular problem. And like the formal proof is somewhat, like, it is not very hard. So you actually I'll just give a sketch of that proof. I'll give a sketch of that proof. Okay. So what is sorting? Like basically what I'm trying to prove is sorting is the most efficient approach. Like it is the optimal approach to minimize the cost. So basically sorting means that if I have sorted the array, then AI less than AJ and BI less than BJ, this holds, right? And we need to minimize absolute of AI minus BI, comma AJ minus BJ. So like what I'm trying to say is that if this is the case, then actually this is better than doing like basically what I've done is I have paired AI and BI and AJ and BJ. Like if this wasn't the case, like basically if I had paired AI and BJ and AJ and BI, then I'm saying that definitely this would give a worse result. So actually you can do some casework, like sorry, this is plus absolute. So I mean what I'm trying to say is that you can do some casework, and like we will see that for all cases basically you need to open this absolute value thing, right? So you'll just take some cases that AI greater than BI or AI less than BI or AJ greater than BJ or AJ less than BJ. Like you will take these cases, and for all the cases you will see that pairing AI with BI is always better than pairing AI with BJ. Like sorting is always the optimal answer. So that is the case here. To minimize that cost, the sum of differences, sorting is always the best. That you sort both the arrays. Like in this case, you might ask that we can only sort one array. We can only change one array, the order. But that doesn't matter. You will just, like, you will sort it. You won't actually sort the array, but you will just match the corresponding elements. Like for example, if the ARR was 312 and BRR was 231, then after sorting, both of these would become what? After sorting, this would become 123 and this would become 123. So but now you cannot sort BRR, right? This is BRR, but you cannot sort it. So instead of sorting, you will just try to rearrange this ARR such that it matches the corresponding elements. like in the sorted order 1 and 1 are matching, so you will try to bring 1 here, and so on. Like you will try to change the ARR and match the corresponding elements. So in that case also the sum would be the same, just that the order would be different, right? But the cost would come out to be the same, and it will be the minimum, because it is the same as the sorted order. So actually, summarizing what I said, either you don't rearrange, right? So in that case, some cost would be, you would be having, which is equal to sum of absolute value of AI minus BI. I mean ARR minus BRR, whatever. And like this is the cost. Or in second case, either you rearrange, right? Either you rearrange, so that will cause you K cost, and then you just sort both A and B, and then you calculate the same thing. So whichever one of this is less, that is your final cost. That is the whole solution. Now, if in any part someone has a doubt, please tell me, and don't hesitate. Okay, so I received no doubts till now. So I'll just explain the code. I'll just show you the code. Like you will, it is self-explanatory. Like after the logic that I have told you. I got wrong answer because I used int instead of long. Like the sum cannot fit into int, so you have to use long. Anyways, so this is the code. Right. Yeah. So ans equals 0, sum equals 0. Now the first case that I don't rearrange, so I just calculate the sum before sorting, right? Okay. So ans equals sum. Like this is one of the answers that I can have. Then for the second part where I rearrange the ARR, so sum will start at k. Like I will bear k cost, then I'll sort both the arrays, and then I'll calculate the cost after rearranging the arrays. I'll increase that sum, and then the final answer would be minimum of sum and ans. Like ans stores before sorting, like the for the first case, and currently the sum stores answer for second case. So I'll return the min of sum and ans. Okay, I'll explain the case where we don't sort. So if we don't sort, then basically let's take the samples. Okay. Minus 795 and 7 minus 2 minus 5. Okay. So if we don't rearrange these arrays, then basically you have to calculate the cost, right? So basically at every index, you need to ensure that the numbers are same, because you need to make these two arrays equal to each other, right? So basically, what would be the cost of changing minus 7 into 7? You would have to add 14, right? Like basically you would have to add bi minus ai. If it is positive, then you would have to add, and if it is negative, then you have to subtract. But in both the cases, the cost would be absolute value of bi minus ai. Like the absolute difference between these two numbers, that would be the cost to convert minus 7 to plus 7, right? The 14. Now to convert 9 into minus 2, you need to do minus 11. So the cost would be 11. And here the cost would be 10, right? So that's why this is absolute value of ai minus bi, and you just take the sum of it over all the elements. Like basically, we don't sort and find the sum, and then we sort and find the same sum, but add k to the cost. So whichever one is less, we'll just return that. Okay. So is there any other doubt? Okay, I am not. Yeah. So let's move on to the third problem. Longest special path. You are given an undirected rooted tree. So what is undirected rooted tree? I mean, if it is rooted, then it is directed, right? But okay, whatever. So it is rooted at node 0 with n nodes, numbered from 0 to n minus 1, represented by a 2D array edges of length n minus 1, where edges of I is ui vi length I, which means that they have given a tree of n nodes, which so it has n minus 1 edges, right? So this indicates an edge between nodes ui vi with length I. Now you are also given an integer array nums, where nums I has a value at node I. Nums I is the value at node I, which means that every node has a value also. So there's a tree where each edge has a weight. Each edge has a weight, and each node has a value. Okay. Now a special path is defined as downward path from an ancestor node to a descendant node, such that all the values of the nodes in that path are unique. Note that a path may start and end at the same node. Okay. So what do they mean? That what is a path on a tree? Like a special path. Special path is a downward path. Okay. So it cannot be like, let's say you have a tree. So let's say you take this path. So this is not special path because it is not a downward path. It has both upward and downward going things, right? So a special path is only downward. It is only like downward. Okay. And also all the values of the nodes in that path are unique. That means that suppose this is the path. So all of these three nodes should have different values. In that case only, we will call this path a special path. Okay. So note that a path may start and end at the same node. Yeah, so it can start and end at same node. So like a path can be like this also, right? And in that case, and basically the length of a path, what is it? The length of this path, that is just the sum of the edges. Like there are these two edges, right? This edge and this edge. So the sum of these edges is the length of that path, and it is special if and only if the all the nodes on this path have different number on it. Okay. Return the length of longest special path, and if there are minimum like multiple, then return the minimum number of nodes in the longest special path. Like I'll show the example. So there is this example tree. Okay, I'll copy it. So there is a node. I'll color code the nodes according to their number. Okay. Uh, this is 0. Then there is this node, which is 1. Then again a white node, just 2. Then red node 3. I think a blue node 4, and a red node, 5. This is the tree, I think. Yeah. And the edge weights 2, 3, 5, 4, 6. Okay, I'll use that next time. Thank you. But right now I can't install it. So, anyways, so yeah, this is the tree given to us, right? Now I have color coded the nodes depending on their number. Like the numbers are, I think the numbers are 2, 1, 2, 1, 3, 1. So this white represents 2, this red represents 1, and blue represents 3. So that is the color coding here. Okay. Now we need to return the longest length of special path, or basically we have to return the length of longest special path. Okay. So basically the constraint here is that um, the path should have all the nodes colors as distinct. So let's say this path is one of the paths. Okay, this wait a minute. So let's say this path is one of the valid paths because it has all the different colors. Then this path is also valid. Then this is also valid, and also this is also valid. So actually in this graph or in this tree, maximum weight is 6. Like the maximum length of a path is 6. Basically these two paths, this path and this path, both have weight 6. Weight, I mean length, like the sum of the edges. 2 plus 4, 6, and the only one edge 6. So the first, like the answer is 6. But also we have to report the minimum number of nodes out of all the paths which have 6 length. So this one has 3 nodes, but this one has 2 nodes. Okay, so that's why we return 6 comma 2, because the minimum number of nodes we want the maximum length but minimum number of nodes. Okay, so that is the question here. Like we want to return the length of the longest special path, and special path is which doesn't have two different colors, right? So actually this problem, actually I've done a similar problem before. So this is actually a very good problem. It is very interesting. So I'll tell you how I thought about it. Okay. So I thought of creating a DP, right? Like you see tree and you think DP on trees, right? So I thought of DP on trees. So like initially I thought that, okay, what if I store the DP of I as, let's say, some node, and the maximum length of path starting at that node and going into the subtree, something like that. Like that is the maximum, like that is my DP. That is, I'll try to, first of all I thought that what if I try to do this DP, that the maximum path length starting from this node, and then somehow maybe I can transition, like maybe if I know the answer of this subtree, this subtree, and this subtree, then maybe I can know the answer to this subtree also. But some complications were there, like I wasn't able to think of the transitions, because the problem was that, okay, like what if, like basically I would think that this has red color, so I don't want any red color, any other red color in my path. So I go down here to this 2 because it doesn't have red color. But the thing is that it's DP, that the maximum length that it stores, it would have red color, right? And I would have no way to know about it. So basically this DP didn't work for me. That if DP, that this is the highest point in that path, that DP didn't work, right? Because I have multiple options. Basically that is the problem, that I had multiple options, that should I take from this, should I take from this, the path, right? Should the path go into this subtree, or this subtree or this subtree, right? So that's why I changed my DP to something like, what if this is the ending node? That if this is the ending node, then till where can I go, right? So that is something that I thought of. Like, if 2 is the ending node, then how up can I go? So the answer is I can go up till 1, because this 0 has same color as 2, right? So that is something that I thought. And then it struck me that I had actually done this problem previously, like a similar problem, similar in the sense that I had done it for an array. Like, actually, it is better if you think about the array problem first. Okay, so let's see that problem. Given an array, you have been given an array, and you need to figure out that does the range L comma R, like you have given q queries. Okay, you have been given q queries, and you have to answer that does the range L comma R have all distinct elements. Does this range L comma R have all distinct elements? Like, this is the query that you have to answer. Like, you have to answer yes or no. Okay, so actually this was a very similar problem that I did. So I knew the idea to this one, so I could extend it to the tree one. So I'll give an intuition about this problem first. Okay, so this problem, how we can do, like, for example, for a particular R. Okay, let's say the array, I'll suppose something, the array 1 2 3 2 4 1, and let's say 3, and then what should I, let's say we have okay, mm, change this to 6, and then we have 1 here. Okay, so yeah, the problem is that we have been given q queries, that from in this subarray L to R are all the values distinct. Okay, so this is the problem. So actually, how to solve this? This is actually a very um interesting thing, that for all R, like for all values of R, you store that how far can you go, like from this particular R, how far can you go back, such that the subarray from L to R contains only distinct elements. Like, for, so let's say R is this, R is here. Okay, so if you go till just this, then it works, only 3 is there. Then if you go these two elements, then distinct elements are there, 6 and 3, correct? Then if you go till here, then 4 6 3, and then if you go till here, then 2 4 6 3. But if you go after this, 3 2 4 6 3, then that is a problem, because these two threes get repeated, right? So basically, you kind of store that for each R, how far can you go. So in that case, for this R, the answer is still here, right? For every R, you try to store that thing. Okay, now how do you store that thing? That is the question. So the thing is, you can actually, this is very trivial, like, now that you know what to do, this is actually, you can think about it. So basically, from this R, problem कब आएगी? When will there be a problem? Like, there's a 3 here, right? So when a 3 comes again, that is a problem. So let's say the 3 came, like, let's say the 3, the last position of 3 was k. Okay, so you definitely cannot go till k, because if you take k, then this 3 will repeat. So you have to go till k plus 1 only, right? So that is one thing. that you definitely cannot go till the previous occurrence of k, previous occurrence of 3, right? You cannot go till here, so you will go till here. But actually there is another problem here. Why? Let's say you have this. Let's say you want to consider this r. You want to calculate for this r. Okay. So what will you say? That the last occurrence of 1. This is 1, right? So where was the last one? It was here. So you will say that you cannot go till k. You will go just till k plus 1, right? But actually this is wrong, because in this range two threes are there. There are two threes. So technically there are two conditions to check. Like, definitely you cannot go till k, but also you cannot go past the answer for this one also. Like, what is the answer for this one? The answer for this r was up till here, right? So if you start from this one, then definitely you can't go beyond this, because then start this value would not be satisfied. Like, basically, if you start from this one and go till left, that is actually a superset of this array, right? If you start from 3 and go left, that is a subset of this starting from 1 and going left. So the answer can only like move to the right. So basically, what is the answer? The answer would be k plus 1, or the answer to r minus 1, like the current r minus 1, and whichever is the bigger, the maximum of these two. That would be the answer, right? Like, basically we do not want this one, so we cannot go till here, we cannot go till k. But also the answer to this thing was up till here, so we definitely cannot go further than that also. So the answer for this r is just k plus 1 comma answer of r minus 1. And you can store the last occurrence of a number in a map. You can just iterate from left to right and store the last occurrence of a number in a map. So you can easily do that. Actually, this problem appeared in ICPC Kanpur regionals. So I don't have any link, but you can search for it. Like, there's some blog on Code Forces, but I don't think you can submit it. Anyways, so I hope this problem solution was clear. Like, if this is clear, then we can just extend it. Actually, we can just use the same method in the tree thing also. So is this solution clear? That what I did, that the answer for r would be max of k plus 1 comma answer of r minus 1. So everyone, is this clear? Or if you have any doubt, you can ask right now. Like, if you have some doubt in this problem, then you can ask. Last step. Okay, just a minute. I'll just clean this. Yeah, so let's assume you have calculated the answers up to here. You have calculated all the answers. Like, what I mean by answer is that how far can you go till the left? Basically, starting, if r is this, then how far left can you go? You have that value. You have the minimum value of L, that how far left can you go. You have that value for every r up till here, and you need to calculate for this r. Okay, so how can you do that? Basically, what is the answer for this r? For this r, I'll just index it. Okay, I'll index it 0 1 2 3 4 5 6 7. So the answer for this r, I mean answer for 6, that is 3, because you can go up till 3, right? So now I want to find the answer for 7. Now look at the seventh element. That is 1, right? So you might think that we can go till like 1 is at 0 position, right? The last occurrence of 1 was at 0 here. So you might think that we can go till here. But actually the problem is that the answer for this 3, like this 3 is repeated, right? So the problem is that the answer for this 3 was only up till 3. Like if you started from r equal to 6, then you could only go till 3. Then how it is possible that starting from somewhere ahead and you can go till here? That does not make sense, right? So actually you can go up till only here, because otherwise this 3 would repeat. So therefore answer of 7 would be max of k plus 1 comma answer of 6, because you cannot go further from answer of 6. Otherwise the like otherwise some elements would get upset. And this k plus 1 here is like k is the last occurrence of the current number. Means 1. No, k is 0. Yeah, like the current number is 1. The last occurrence of it is at 0. So k plus 1 is 1. And the max of 1 and answer of 6, which is 3. So the max would be 3. So the answer of 7 is 3. We can go up to 7 to 3. Like we can, if we end at 7, then we can go up till 3. So is that clear? Like, do you have a doubt? Clear. Okay, cool. So I am assuming that no one else has a doubt also. So okay, I'll try to generalize this for a tree. Okay. So yeah, the thing is that we want to find the longest path, right? The longest path which has all distinct values. So that is actually the same thing as this array problem. We for an ending value of r, we had to find the longest subarray such that all the elements are distinct. So we can apply the same logic here. That um, let's say I want for this like for this node, I want the answer that how up can I go so that um, so that all the values on that path, or in this case all the colors, are distinct. So for this 2 I can store that I can go till this 1. This is a path that I can go. So actually you can apply the same logic. Like if you have the answer for this 1, then basically like you, like in this case you were checking the last occurrence of 1. Like for example, if you want to find the answer for this 7, then you check the last occurrence of 1, which was here. So k is here, right? So in this case also, if you want to find the answer for this 2, this is white node, right? So you need to find the last occurrence of white node. So the white node is at position 0. It is at level 0, right? So that's how far you can go. Okay. Actually, that's not how, like basically you cannot go till there. You can go up till next of here. And also, yeah, so the same idea that you can go till next of this thing, but also you have to respect the parent. Like here you did max of two things, right? Here you did max of k plus 1 and answer of 6. So like answer of previous element. So here also you will do the lower, like you will choose the lower node of whatever, like last white node and the answer for this node. So what is the answer for this node? The answer for this node is like if you start at 1, then you can go till 0, right? This is the case. You can take this whole path. So the answer for this 1, that would be the 0 node. And so like to calculate for this 2, you can actually check the last white occurrence. So the last white occurrence is this. So you can go till here. And the maximum of those two is basically this thing. So like this is the idea here. The implementation is a bit tricky for this, but this is the idea that you check the parent and you look at the last occurrence of a particular color. What will it be for 4? Okay, so for 4, there is no blue for up, like there is no blue up there. So you just need to check its parent. And the answer for its parent is it can go up till here. So 4 also can go up till here because its parent can go up till here because there is no blue. Nothing else is stopping it from going up till here because there is no blue in this path. Suppose there was some blue, then we would have to take the maximum of those two, right? So that would be the answer for 4. Like 4 can go up to 0. So that is the idea here. And then you can just like to find the answer, you can just iterate over all the nodes. Like you want to find the longest path, right? So basically the longest path will end at some node, right? So you will iterate over all the nodes and check that what is the length of their longest path. Like till where can this 5 go to? It can go till 2. Till where can this 2 go? It can go till 1. Till where this 3 can? It can go up to only 3 here. It cannot go even 1. Then till where can this 4 go? It can go up till here. Till where can this 1 go? It can go up till here. And do I have something left? It high. So yeah, that is done. And this 0, it can go up to 0 only. So out of all these 6 nodes, whichever is the longest path, you will select that. And if there are multiple longest paths, you will select the one with smaller number of nodes, with lesser nodes, right? So this is the question. Like this is the idea here. And your implementation might differ. Like there are many ways to implement this. But basically, the idea for implementation is you will run a DFS. Okay. So wait. What happened? Yeah, so you will run a DFS on this tree. Like basically, you start from this parent. Okay, you start from the root. Then you evaluate this answer. So the answer for root is obviously just it can go up till itself, right? That is the answer for the root always, regardless of whatever downward there is. So the answer for root is this. Now you go down. Okay. And actually you have to keep track of a map. You have a map which keep tracks of last occurrence of every color. Okay. So what you can do is you will maintain this map while you are doing DFS, right? Sorry. So basically, before you move to this one, you will put this 0 in this map. That the last occurrence of white was at this node 0. Then you will go to 1. Now you will calculate the answer for 1. To do that, you will check its parent and check that whether red has occurred. Has red occurred anytime before this or not? So if there is something in this map which is red, like if there is some red occurrence in this map, then you will take the maximum with the parent's answer and the map. Okay. Then so you have found the answer for this one. Then you will go to this 2 and sorry, you will put this into the map. You will put the red node into this map. Now you will go till 2. So you will go to 2 and you check that there is a previous occurrence that of white. A white occurred here. So you can only go till here. And also the answer for this one was this. So maximum is this node. So yeah, so that's how you do. That is the DFS. Like this is, so yeah, this is the idea for implementation. Now I've actually skipped over many things here, that the implementation details, but I'll explain them when I'll show you the code. So is the idea clear? Yes. So you will do a DFS and you will maintain a map, and the map which will store. Yes, next step, we will replace the white value with 2, because when we go to this 5, the last occurrence of this white value is 2 and not 0. So yes, you update, like whenever you go to a child, you will update the colors value to that node. But also you have to make sure that when you come back to this node, like after you have done DFS on this subtree, when you come back and when you go up, so before going up, you have to reset it. You have to again set the value of white to 0 as well. So that is also one thing that you need to ensure. So before calling this DFS, just store this value in a temporary variable, and after you come back, just revert the changes. Okay. So, yeah, that is the idea. Can I repeat this part? Sure. So basically, the thing is, we are at 0, right? Now, we will go till, so for we'll store the answer for 0, and then before going to this 1, we'll store the we'll store map of white as 0. The last occurrence of white is at the node 0. Then we'll go to this 1. Now we'll calculate the answer for this 1, and we'll store the answer for red, or the last occurrence of this red, as 1. Then you go to this 2, right? So you calculate the answer for 2, and then you store this 2 in the map. Like basically, initially the answer for the last occurrence of white was 0, but now you change this white occurrence to 2, because there is 2 here. So now for this 5, the last white occurrence is at 2, not 0, right? That's why you change it to 2. That's why when before going to 5, you change the occurrence of white to 2. Now the thing is that when you are returning, let's say the DFS for this subtree, this 5 subtree is over. Now you return to 2, and then you return to 1, because there are no other children. So before returning to 1, you actually have to ensure that the value for white is again changed back to 0, because yeah, okay, got it, then it's good. Nice. Can we keep vector of vector and pop back instead of map, since if rank constraints are tight, it might give TLE? uh like vector of vector, it is not necessary actually. Like storing a temporary variable is just O of one space and per, like yeah, it is just O of one, and when you come back you can revert it. And like instead of map you can use a vector, because the colors are up till 45, right? The nums are up to, sorry, 5e4. Nums are up to 5e4. So instead of a map you can use a vector of length 5e4 to avoid the login factor. That's the best you can do. So yeah, this is the idea, but actually the implementation is also pretty tough, so I'll try to explain that. So I'll explain that using the code. Okay, actually before explaining that, I'll just explain you what I have stored actually. Okay, so in this map, um actually what I have stored is that what I need to subtract. I'll explain. Wait. So I'll try to erase all of this. Just 1 second. Okay. Yeah. So as you can see, so okay, guys, let's just change it to some other good color. Let's say okay, yellow. Yeah. So suppose you are at this 5 here. Okay. Why didn't it change? Okay. So let's say you are at this 5 here. Uh, this is annoying. All right. Yeah, this is better. So you are at this 5 and you need to calculate the answer for this 5. Okay. So the last occurrence of the 5 was this 1, right? So definite the answer to this 5 would be 6, right? Because it will go only up till 2. Okay. So actually, while doing DFS, I maintain two variables. One is the current edge weight sum, and other like this is one, and the other is number of nodes. Like basically, while doing DFS, I have these two parameters as well. Like in I have V and parent. Like normally in DFS we do V and parent, but also I have these two variables that I have stored. Basically, when I'm calling, suppose I'm calling DFS from this 0, then I add 2 to the edge weight sum, and one node I'll add. So that's what I'm keeping track of. So when I reach here, when I'm doing DFS like this, and I reach 5, the edge weight sum, what is it? 6 plus 3 plus 2, it is 11. Edge weight sum is equal to 11, and the number of nodes. Actually, I start from 0. Okay, so this is 0, this is 1, this is 2, this is 3. So the number of nodes, that is equal to 3, right? And now we want the answer for this 5, right? Wait, I'll just delete this also. So yes, what I actually had done was that I kept these two variables, the edge weight sum and the number of nodes. So when you reach this 5, the edge weight sum would be 2 plus 3 plus 2, 2 plus 3 plus 6, right? That is 11. And the number of nodes is 3 because I started from 0. So 0, 1, 2, 3. Now, to get the answer, I actually need to subtract. Like basically, the 5 can go up till here only, right? So I need to subtract this 3, this one node, this 2, and this another node. I need to subtract these 4 values, right? So to do that, I have just actually I have also created one limit. Like I have also created one another variable that where can we go? Yeah. So basically, I have created some maps or some arrays. One array is the answer array. Answer array just stores the path length and number of nodes, and one is the one I have created the lim variable. Lim means that till where can we go, and it stores the same thing, that it stores the path length and the number of nodes. But actually, it stores that how many we need to subtract, like what do we need to subtract to get the answer. So like basically for this 5, the edge is 11. The sum of edges 2 plus 3 plus 6, that is 11, and number of nodes is 3. So actually we need to subtract 1 from the number of nodes and this 2 plus 3 from the edge weight to get the answer. So the lim for 5, that would store this 2 plus 3, like the lim for 5 would be this. Sorry, lim for 5 would just be 2 plus 3, which is 5, and the number of nodes, which is 1. So actually this might not be very clear right now, so I'll do explain the code. Okay, I'll just show you the code. Hmm. Yeah, so basically I have this function here. So this is the function that we have to fill. So n is nums dot size, like I just defined n as nums dot size. I have these global variables adjacent, dp and lim. Okay, I have this adjacent, dp and lim. Actually dp stores the answer for the current, like what is the length of longest part ending at some node, that I'm storing in dp. And this adjacent is just adjacency list of the tree, and lim is just lim just stores that what I need to subtract. So I'll explain that in a minute. And this val is just nums, it is equal to nums. I made a copy of it here. And this last is the map that stores the last colors, like it stores that where was the last white or where was the last red. That's what it stores. Okay, so this is the map. So I initialized this adjacency, I made this adjacency list. So for x in edges, adjacence of x0 dot pushback x1 x2 and x1 dot pushback x0 x2. Okay, now I do dfs. So yeah, I did dfs. So actually that dfs filled up the entire dp. Okay, and after filling the dp, I just found out the answer. So I initialized the answer with dp of 0, that is the answer for root, like the node 0, the answer for node 0. And then I just looped through the all the nodes, and if the dpi dot first, that is the length, is greater than ans dot first, like if it is greater length, then ans equals dpi. And if it is equal but the number of nodes is less, then also I do ans equals dpi, and I return the ans in the vector form. So actually now whatever is remaining, it is only the dfs function, right? So it is actually something, it looks complicated, but actually it is very simple. Okay, so I'll explain. Right, so I did dfs on 0, parent is -1, the number of nodes is 0, and edge weight is 0. So the parameters are this: v is the vertex parent, the number of nodes, and len is the sum of edges, that is length, right? So first I check if the parent is -1. If parent is -1, then like it is the root node, so I handled it separately. So dp of v, the dp of root, like the length would be 0 and number of nodes be 1, right? And lim of v would be equal to 0 comma -1. That I'll explain in a minute why I have set it to 0 comma -1. And last of val of v, basically the last occurrence of the color, the current color, that is at 0 comma 0. What is the 0 comma 0? um just a minute. Yeah, so actually it is, I'll explain that also in a minute. So last of val v, it just stores that this is the node at which this white last occurred. So last of this white color is equal to 0 comma 0. I'll explain what is 0 comma 0 in a minute. So I just did DFS. I looped through the childs, and yeah, in the last value dot first, I plus equals wait. Okay, so basically I looped through the edges of this 0. Okay, right now I am at 0. Now I looped through the edges of this 0. Okay, and then I went at this 1. So before going to this 1, actually I increased the last dot first, like last of val v, which is last of white dot first by weight. Like basically I'll try run this code once. uh Sorry for the delay. Yeah, so I'm at 0, right? Right now the last of this color is 1. Last of 1, this is right now 0 comma 0. Okay, now before going to this 1, I increase this variable to 2. Like I increased it by 2. Like basically I increased the edge weights. I added this 2 to the edge weight before going to this 1. Now I went to this 1. Okay, then last of 2. What is last of 2? This is red is 2, right? So last of 2, actually that is um basically the sum of weights still here, like 2, and the number of nodes, that is 1, right? And then before I go, like after that I go to this 2. So if I go to this 2, I add this 3 to last of 2. So I add this 3 to 2, which is 5. So now you will understand why I did that. Okay, now you are at this 2. You are at this 2, and right now the len variable is equal to 2 plus 3, which is 5, and the number of nodes equal to 2 right now. Like the DFS, in the DFS call, this nodes and len, these two variables, that's what the value of them is. The len is 5 and nodes is 2, because 2 plus 3, which is 5, and the number of nodes 0, 1 and 2, right? That is what I have done. Now you will see that this white actually appeared before, right? So you need to actually subtract these nodes, like this node and also this corresponding edge. You need to subtract, because you can go up till only 1. So that's why I added this edge weight into this last of 1, so that when I subtract this last of 1, it automatically gets subtracted. So when I subtract this len minus 2, so it will become 3, and nodes is 2. So I do 2 minus 0, so it becomes 2. So yeah, this is the correct answer, that this path has 2 nodes and length is 3. So that's why I added this edge weight of 2 to this last of 1 before I did DFS, so that when I subtract this white color, um, I'll subtract this 2 edge weight also, right? So I'll explain the other cases also. So yeah, this was the case for the root, that I looped through the children, and last of value dot first plus equals weight. Like I added this 2 to edge weight custom and did DFS, and then I removed it. Like before going up, I removed it, and yeah, last dot erase. Like this doesn't matter because this is the root only. Now, if this is not the root, suppose it is the inner children. If it is not the root, then if last dot find val v is not equal to last dot end, what that means is the current color that you are at. This current color, it is not the first time that you have come. Like this is not the first time you have visited this color. Like this white has come before. It has come before, right? So you will see that lim v is basically where can I go till, like what is actually, it is basically the max of lim parent and last of val v. So it is actually similar to this thing, right? The max of k plus 1 comma answer of r minus 1. So the answer of r is max of k plus 1 comma answer of r minus 1. So lim v is equal to lim of parent comma last val v. So actually this lim stores that what I need to subtract. So so the answer would be this current edge length minus lim v dot first. So this I subtract this lim v and the current node minus lim v dot second. Then I do the DFS for the children. So this is the answer. I calculated the answer for the current node. Now I'll do DFS for the children. But before doing that, I need to update this last value. Like I need to update that this white occurred here. Before going to this 5, I need to update the position of this white. So last of val v equals make pair len nodes. Like I stores the current length of the path and the number of nodes in the path. So I update this last, and before updating it, I store the value in a temporary variable. Then I do the DFS the same thing. Like before calling the function, I increase the first by WT. That is the edge weight. So before going to this 5, I increase the edge weight by 3. Then I go to this 5 and then I decrease it. I undo the operation. And after this whole DFS is over, I just do last of value equals to temp. Like basically I restored the previous value before returning. Before I return, I restore the previous value because the color occurred previously. And otherwise, like if the current didn't occur previously, then lim of v equals just lim of parent. Like similar to this case, that basically if in the array the current number, suppose there is 3 here and you are calculating for this 3, and if 3 didn't occur anywhere before, there is no 3 here, then definitely the answer for 3 would be just answer for r minus 1. Like answer for r would just be answer for r minus 1. So similarly here, the lim of lim of v is equal to lim of parent. And again, I calculate the answer for this v, that is just len minus lim of v dot first, comma nodes minus lim of v dot second. And then I update the last of value of v. Like same thing, that I update the last map and then I do DFS. And then I erase from the last map. Because before going to before returning, I need to undo my changes, whatever I have done. So since I have inserted this val v, I need to erase it right here. As you can see that here we didn't erase it, we restored it to the previous value because there was something previously here. There is something like the val v has occurred before. So therefore we restored it to previous value. And in this case, it hadn't occurred before, but so yeah, that's why we are erasing it. So actually this code is somewhat complicated and this problem is very, very good, right? So it might take some time to digest it. So I suggest that you all go through this code and like kind of dry run it, okay? And like keep in mind that this lim v is basically what you need to subtract from the current count, the current node count and the current edge weight. So this is what this is what you need to subtract. So keep that in mind and try to dry run the code by yourself. So I think that that would help you to understand this code better. And if you don't understand, then you can just ask in the doubt section of the TLE or the YouTube comments if you are watching on YouTube. Okay. So try to dry run this code by yourself. All right. And yeah, anyways, so I'll move on to the next problem. unless someone is out in logic. Like the code is actually pretty difficult to understand in just one go. So I encourage you to go through it once more at your home, like by in your own time. But if someone didn't get the logic, then I can explain it right now. Okay, so I'm assuming that you got the logic. So I'll move on to the next problem, right? So actually, this problem was easier than question number three, as you can see by the solves also. 1.3k solves for this one, and for the previous one, it had 1.1. Okay, in the contest, like the fourth one has had double problems when I checked it. So okay, the problem says that you are given three integers m, n, and k. There is a rectangular grid of size m by n containing k identical pieces. Return the sum of Manhattan distances between every pair of pieces over all valid arrangements of pieces. A valid arrangement is a placement of all k pieces on the grid with at most one piece per cell. Since the answer may be large, printed modulo. Okay. So the problems for PNC, it is a simple, like not a simple, but it is a good PNC problem. So the problem says that basically you have a grid. You have a grid of size n by m or m by n, whatever. There are some rows and some columns. Yeah. And you have k coins, right? So, and you have to put them on this grid, right? So there are n into m cells, n into m total number of cells, and you have k coins. So there are total n into m ck ways of putting these coins onto this grid, right? So over all of these ways, you need to calculate the sum of Manhattan distance. You need to calculate summation of Manhattan distance of all the pairs in each arrangement. Like let's take the samples. I'll explain the question using samples. Okay. So let's say nm are 2 and k is 2. So it is a 2 by 2 grid and k is equal to 2. So in total, there are actually 4c2, which is equal to 6 ways to arrange these two coins on this board, right? And for all of those arrangements, you need to calculate sum of Manhattan distance. So they have actually done explained it very, very well. So there are 6 possible arrangements. So if you put these coins in this way, so in the first 4 arrangements, like the distance is 1. Distance between this and this is 1. And in this last 2 arrangements, it is 2. Like between these two is 2 and between these two is 2. So the answer would be 1 plus 1 plus 1 plus 1 plus 2, which is equal to 8, right? And they have given another sample that m is equal to 1, n equal to 4, and k is equal to 3. So there are 4 arrangements like m into n c k, 4c3, which is 4. 4 arrangements of placing the coins on this board. So for the first arrangement, you need to consider all the pairs and add up their distances. So considering these two pairs, distance is 1. Then these two distance is 1, and these two, the distance is 2. So in the first arrangement, the sum of distance is 4. Then similarly, second one, sum is 1 plus 2 plus 3, which is 6. And you can easily see that the third one also 6, and fourth one is also 4. So the answer is this, the 20. So I think the question should be clear. Like someone who is trying to attempt the fourth problem, the problem should be clear to them. Okay. So actually, what you can do is you can use the method of contribution in this. Like let's say we have a grid, right? Let's say a 4 by 4 grid. and there is some k. I don't know what is k, but let's say it is something. So the grid is 4 by 4. Now we have to calculate the sum of distances, right? So I am asking, like, okay, the distances that have to be the distances that we are taking, they have to be between those two cells which contain coins, right? We only consider those cells which contain some coins, right? That's the thing. So let's say we want to calculate that the distance between this node and this node. What is it? It is 3, right? The distance is equal to 3 between this node and this node. So we need to count. Suppose we want to count that how many times in the final sum, how many times does this distance occur? Like this distance of 3, I mean, not this is just root 5. This distance of 3, like the distance between these two cells, how many times it occurs? Like if we know that, we can just multiply by 3. We can multiply that value by 3 and add it to our answer. And we can do this thing for every pair of cells and we'll have our answer. But you will say that n square is not allowed because m into n has constraint up to 1e5. But yeah, I will get to that. But I'm building the solution right now. So one thing is that we need to, like, what if I ask you that in how many arrangements does this decision occur? Like how many times will this 3 get added? Like corresponding to only these two cells, not all the threes, just these two cells ka distance. When will it be added to our answer? How many times will it be added to our answer? So the thing is that for it to be added to our answer, definitely there should be a coin there. Like there has to be a coin here and there has to be a coin here, right? So we need to count the number of arrangements in which there are coins here and here. That's what we need to do. It is that simple, that we just need to count the number of arrangements in which there is a coin here and here. So that's how many times this distance will be counted. Is that clear? Is this part clear? Yes. Okay. So just we need to count that in how many arrangements there will be a coin on this cell and a coin on this cell. So basically we had k coins, right? We had k coins and we put two of them here. We put one of them here and we put one of them here. So how many are left? We are left with k minus 2. So we need to put k minus 2 coins on the remaining cells. So initially there were m into n cells, but we filled 2. So we are left with mn minus 2 cells, right? And we need to fill k minus 2 coins in them. So the number of ways would just be mn minus 2 c k minus 2, right? So this is how many times this value of 3 would be added to the answer. And we just need to do it for every pair of vertices, every pair of cells. So actually you can see that this value, like the number of times uh, this 3 is added, and it actually doesn't depend that which two cells we are taking. This mn minus 2 ck minus 2, this is a constant value, right? So for any two cells that we take, their distance will get added this many times to the answer, right? So um therefore we can just actually count, like, basically what I'm trying to say is that you choose two vertices, you find their distance. Suppose it is d, then you multiply it by mn minus 2 ck minus 2. So this is suppose dij, the distance between ith and jth cell, and then you take the sum over all ij, right? You will get the answer. But instead of doing this, what if you just take this out of this summation? You just take it common. So you will do mn minus 2 c k minus 2, because this value doesn't depend on this diz, right? So you can just take it as common, and then you can just find this diz ka summation. I is equal to 1 to mn, j is equal to I plus 1 to mn. Like basically all the pairs of cells. There are mn cells, right? So you need to find the distance. You need to find the sum of distances between all pair of cells. That's what it boils down to, right? And then once you have found that out, you can just multiply it by mnc2, sorry, mn minus 2 ck minus 2, and then you will have your final answer. So the problem boils down to find Manhattan distance between all pairs of cells. What was my thought process? Uh, the thought process was that, like, we can exploit this thing now, that we have to find over all valid arrangements. Like overall, that means there is some symmetry. Like the the technique that I used, it is called actually contribution technique. The contribution technique. Contribution technique. So basically, in this technique, we just check that if we want to find the sum, then we can just break the sum into different parts and check that what is the contribution to the sum. So I just check the contribution for each pair of vertices, and that turns out to be their distance into mn minus 2 ck minus 2. So in PNC problems, it's actually a very useful technique that you find the contribution of each particular element in the sum. So yeah, so the problem boils down to find the sum of Manhattan distances. Wait, find sum of Manhattan distances between all the pairs of cells, right? So you can easily do it in n square. I mean mn whole square, right? You can just iterate from I to j, like you can iterate over all the points on the grid, and then add up their distances, and then you multiply it by this thing. But O of n square doesn't work here because the constraints are tight, like they are 1e5. Okay, so we need to do something else. Okay, so what do we do? Actually, we can think about it. So basically, we can, it is actually now mathematics. It is really simple mathematics. So what we need to find is, let's say this is a 4x4 grid. Okay, or let's take 4x5 grid to make it somewhat generalized. So I'll mark it 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So actually, what you need to find is, if I write a summation, um, summation from I equal to 1 to 4, summation, or let's say not I, I'll use a better variable, x1 equals to 1 to 4, x2 equals to 1 to 4, summation y1 equal to 1 to 5, and summation y2 equal to 1 to 5. And you need to find this summation for mod x1 minus x2 plus mod y1 minus y2. Like this is what you need to find, right? You need to find that over all the points. These four summations, like basically you can think of these as for loops. These four for loops iterate over all the points, all the pairs of points. Actually, it iterates over a comma b and b comma a. Like it counts them twice. So actually, you need to divide it by 2 also to get the answer. But actually, this is what we need to solve right now. That there are four for loops: x1 from 1 to 4, x2 from 1 to 4, y1 from 1 to 5, and y2 from 1 to 5. And the distance between them would be just x1 minus x2 plus y1 minus y2. So is this part clear that how this came? Yes. Okay. So actually this summation, you just need to simplify it. And simplification is, I think, pretty simple. Basically what you can do is you can separate these two parts. Like this x1 minus x2 part, you can do it separately, and y1 minus y2, you can do it separately. So let's say I'll tell you how to calculate for x1 minus x2. Okay. So I'll take n and m instead of 4 and 5. So let's say you take x1 minus x2 part. So x1 from 1 to n, summation x2 from 1 to n, summation y1 from 1 to m, and summation y2 from 1 to m. And you need to calculate, suppose x1 minus x2, uh, x1 minus x2 ka mod. You need to calculate this sum. So if you can see, this x variable is independent of this y variables. These two y variables, they don't interfere with this. So you can actually take this out of these two sums here, right here. So I'll write this as summation 1 to n, x2 from 1 to n, and I'll write mod x1 minus x1 minus x2. And then we have into summation of y1 equal to 1 to n, y2 equal, sorry, 1 to m, 1 to m, and y2 equal to 1 to m of 1, right? Like I took the x1 minus x2 common. So here 1 was left. So this sum is actually m square directly, right? So we can write this as m square, summation x1, and actually m square. So I'll just rewrite this here, um, m square, and then you can bring this m square out of these two summations because they don't depend on x1 and x2. So it simplifies down to m square, summation of x1 equals to 1 to n, summation x2 equals to 1 to n of mod x1 minus x2. Okay. So here comes the interesting part now. Now, basically, if you can see, I'll show you by example. Like, basically, what it wants us to do, it wants us to take all the ordered pairs from 1 to n. Like, it wants us to take 1, 1, 1, 2. What happened? Just 1 minute. My laptop is glitching. Yeah. So 1, 1, 1, 2, and up to 1n. It wants us to take. And also, it wants us to take 2, 1 or 2, 2, and up to 2n, and so on, like n1, n2, and nn. So it wants us to take all of these ordered pairs of x1, x2. It wants us to calculate the distance between these two. Like, for suppose this is 1, for this one it will be 1, it's 1 0 and so on, and it wants us to add all of these values up, the absolute differences. So actually we can make a neat table of this. So let's suppose value of n is 4. Okay, so to visualize this, I'll make a table. So here is a value of x1, this is value of x2, and the value of n, let's say, is 4 right now. So 1 2 3 4, 1 2 3 4. So difference between, so basically in the cells I'm writing the value of mod x1 minus x2. So here it will be 0, here it will be 1, right, 1 1 1 1 1 1, 2 2 2 2 and 3, and it wants us to find the sum of all of these numbers, right? So to do that, actually you can observe one thing, that these numbers are same as these numbers. Like, it is the mirror image, right? It is the mirror image about this line. So we can actually calculate the sum of these numbers and just double it, twice of that amount, right? So we find the sum of these numbers. Now how to do that? How to do that? You can observe the pattern here. You can observe the pattern here, that how many times does 1 occur? 1 occurs 3 times, 3 into 1. Then 2 occurs 2 times, 2 into 2. Plus 3 occurs 3 times, 3 into 1. And you multiply this by 2. So the sum would be 3 plus 4 plus 3, 10 into 20. So for n equals to 4, the sum is 20. But what if we want to generalize it? Suppose we want to generalize it for n. So just imagine, if you make an n by n table like this, you made a 4 by 4 table, right? But if you make an n by n table, so here all would be zeros. There would be n zeros, right, in this. Then how many ones would be there? Can you tell me how many ones would be there? In this case, there are 4 zeros and 3 ones, then 2 twos and 1 3. So as you can see, the number is decreasing. So in case of n by n grid, there would be n zeros, right? So how many ones would be there? N minus 1 ones would be there, right? So you can just write n minus 1 ones would be there. N minus 1 into 1 plus how many twos would be there? N minus 2. So n minus 2 twos would be there. So and so on. And you can write this as like, wait, I'll write it like, the last term would be n minus 1 into n minus 1, and yeah, into 2, whole thing into 2, don't forget about that. So we need to calculate this sum right here, and this sum I'll write it in terms of summation note, like that notation. So this is equal to I equal to 1 से लेकर n minus 1, this is n minus I into I, right? And yeah, into 2. This part should be clear. So I can write this as, I'll just write 2 at the outside. Now this is n into summation I equal to 1 से लेकर n minus 1 into I minus summation I equal to 1 से n minus 1 of I square. Like basically I just opened this bracket and I brought this n outside the summation and I split the minus sign over the summations. Okay, so this is what it becomes, and this is just sum of first n minus 1 natural numbers. That is, this is just n into n minus 1 by 2. And this is sum of first n minus 1 natural numbers squared, square of natural numbers. So that actually turns out to be like the formula is I equal to 1 to n of I square. That is actually equal to n into n plus 1 into 2n plus 1 upon 6. So instead of n, we have n minus 1 n minus 1 here. So we can put n minus 1 instead of n. So we will get n. So n minus 1 into n to 2n plus 2n minus 2 plus 1 is 2n minus 1 upon 6. And also is an n here. And there's a 2 outside. And there's a minus sign here. So I'll simplify this thing. As you can see, n into n minus 1 is common here. So we can bring it out. And we can cancel out this 2 also. So n into n minus 1. अंदर बचा n minus 2n minus 1 upon 3. So this turns out to be n into n minus 1 into 2n minus 1. Sorry, not 2n. N into n minus 1 into n plus 1 upon 3. So what is this actually? This is the value of this summation. This summation is n into n minus 1 into n plus 1 by 3. And with that, there is some m square also. Like basically, this m square is also there. So finally, the sum, like the x distance, that is equal to n into n minus 1 into n plus 1 into m square divided by 3. So similarly, if you think the y distance would be equal to m into m minus 1 into m plus 1 into n square divided by 3 by symmetry, right? And so therefore, the sum of distances of all pairs, that would just be the addition of these two things. But actually, in this case, we are counting each pair twice. Like this is a summation, right? This quantity is the value of the summation, this one, right? But this summation counts all the ordered pairs twice. Like it counts 1 comma 2 and 2 comma 1 differently. Like basically in this grid, it counts like this cell and this cell, or this cell and this cell differently, right? So therefore we need to divide it by 2 also. So we just divide by 2, so it will become by 6. And then finally we'll multiply it by nm minus 2 ck minus 2. Like this is what we discussed, that it is just where was it? Yeah, dij into like, yeah, it was nm minus 2 ck minus 2 into summation of dij. So therefore this is the answer. Yeah, so n into n minus 1 into n plus 1 by 6 into m square plus m into m minus 1 into m plus 1 into n square by 6. Like this is the addition. This whole quantity multiplied by nm minus 2 into nm minus 2 ck minus 2. And you need to calculate this mod m, like modulo 10 raised to power 9 plus 7. So which I think you all, like you should be knowing how to do that. If you don't know, do you know? Just if you don't know, I'll explain. You don't know. Okay. So, uh, yeah, sure. So I'll explain. Do you know that how to do multiplication and addition in modular space? Like, if you want to calculate AB mod m, then you can just calculate A modulo m and B modulo m, and yeah, and just take mod m. You know this. So, and do you know modular inverse? No. Okay, so basically, um, A plus B, A minus B, and A into B. These things can be done directly and just take mod m. But A divided by B, sorry, wait, uh, A divided by B has nothing, like you cannot, like the way to do this in modular field is to multiply A by B inverse, like the multiplicative inverse of B in mod m. Like what is B inverse? B inverse is such that B into B inverse should become 1, like modulo m. So for example, if m equal to 7, let's say m is equal to 7 and you have b is equal to 2, then what is B inverse? uh I'll just tell you. B inverse is, what would it be? 3 4 4, it will be 4, right? Like if you multiply these two, 2 into 4, which is equal to 8, but mod 7, that is equal to 1. Therefore, uh if b is 2, then b inverse is 4. So suppose you want to find 3 by 2 mod 7, then you would actually do 3 into 2 inverse, which is equal to 3 into 4, which is equal to 5, like which is equal to 12, but mod 7 it is 5. So that's the concept of modular inverse. But how do we calculate it? We can just calculate it using Fermat's Little theorem. Like that theorem states that if there is suppose we have a b and we need to, like b raised to power p minus 1 is equal to 1 mod p. This is the theorem that if b and p are co-prime, then v raised to the power p minus 1 is 1 mod p. Like this is the theorem. So therefore, if you write this as b into b raised to power p minus 2, like that is also equal to 1. So therefore, if you observe, this b raised to power p minus 2 actually is b inverse. B raised to power p minus 2 turns out to be b inverse. So if you want to calculate this b inverse, you can just take the power to b minus 2. So if I show you the example here, like if I wanted to calculate b inverse for 2, then I would just calculate 2 raised to the power m minus, like 7 minus 2, which is 5, which is 32, and mod 7 it is like 4. So that's how it works. So now if you want to calculate n, like you want to calculate this value, right? uh, you got it. Okay, but I'll still complete my explanation for the YouTube audience, that here you need to multiply n minus 1, and n plus 1, and m square. So multiplication you can do normally, but for division you will multiply by mod inverse of 6. Like you will multiply by 6 raised to power p minus 2 or mod minus 2, and the same thing you will do here. And for NCR, same thing. Like formula for NCR is what? NCR is n factorial divided by n minus r factorial into r factorial. So these divisions, you will actually do inverse multiplication, like mod inverse. Okay. So that's how you calculate. Now I'll just show you the code. Actually, the code is just formula. Like I made these functions to help me. Like this is the power function to calculate a raised to power b mod, like modulo 10 is 9 plus 7. So it's just using one exponentiation, which everyone knows. Smart multiplication, like yeah, this is self-explanatory. And mod division, I just multiply the inverse of b. Okay, so now this is just an implementation of my formula. Like I calculate the factorials over here. This ans is just n minus 2 c k, nm minus 2 c k minus 2. And then this ans 2 is this thing right here, this first term. And this ans 3 is the second term. And then I return uh, ans into, like, ans multiplied by ans 2 plus ans 3. So yeah, I think it should be self-explanatory. Did you get the code? All right. Cool then. So, do you have any doubts? Any other doubts related to any other four problems? Okay. So I guess I'll end this. I'll end the meet then. Thanks for joining in, and thanks for watching for the YouTube audience. Good night, everyone. Bye.